Alright, so this is the last class, and we're going to be using Prolog. We'll be using assembly language to implement Prolog programs in addition to C++ programs. No, I'm just kidding. I'm just kidding. Although that wouldn't be too much. That would not be too much to do. Yes, I think I'm on Discord now. Okay, so that's fine. Not a problem. Yeah, I had to restart my browser. Just when I was starting Google Calendar, it just crashed on me. But it had been running for a few days already. Most of my Windows, run for a few days at least. My uptime is usually pretty high, so it's about time to get it restarted. All right. So what we're doing today is we are doing the practice exam. The YouTube should be running now, unless it also got discontinued. Nope, it's running. I think it's running. There's no link. Oh, okay, right. Okay, so I see. Yes, it has been going, but it's in the public, side, so you can actually watch it from my general channel. Even without the link, you can still do it. I know you guys are used to having that link. Oh, there we go. Thank you, Yan. All right. So, right. So we are going to work on two sample exams today. Well, we'll work on those one at a time. Okay. So we're not going to be working on all of them at the same time. So let me get to my terminal first. Okay, and of course the one that I want to use is always the last one. There we go. All right. So we're going to work on let's see. The text files, for today. So there are two. One is a debug thing. The other one is the implementation thing. Which one do you want me to start with? Okay, there's the question. You already. Oh, you want the debug one? Okay. Anyone else? Okay. All right. So I guess the debug one is the popular choice for some reason. Okay. All right. We can do it. Ah. Okay. Yeah, I just got my coffee ready because there was a uni meeting right before this class. So it was good. It was a good meeting, but it does push my time a little bit. Um, there we go. All right, so this is the debug one, I think. So it has the C code and then it has the assembly code, and we're supposed to debug it. All right, debug. Yes, I like that. All right, so let's go ahead and debug this program. I'm gonna split this screen so this way I can stay in the view of the C code on one side and look at the assembly code on the other side. So the C code is right here. Begin C code, and there's an end C code somewhere else. And so we'll start with the C code on this side. And then when we are done with just mentally debugging the program, we can actually run the C code. The C code is runnable, and that's part of the whole reason why I give people the C code is they can use the C code to understand how the program is supposed to work. All right. All right. So on the right hand side window where the cursor is right now, we are looking at the assembly code, and the assembly code starts here. Okay, so this is the beginning of the assembly code. We have the usual no op, and then we have a LDIC main, and then JMPC. That is actually okay because these two instructions. Let me turn on line numbers so we can refer to the line numbers. So line 82 and line 83 together, they basically just do a JMPI to main. That's really the same thing. Okay, and I would like to turn on syntax highlighting. So if you guys don't mind, I'm gonna exit and then change the file extension to TTP-ASM, and then we'll go back in, because syntax highlighting really kind of helps in some way to help debug this program. And I'm also going to change the name to debug.ttpasm just so that it's easier to read. There we go. And once again, we do a V split. And then on the right hand side, we start with the assembly code. There we go. All right. The link to the file is from the general channel. So in the general channel, there are a few files that I specified over there. I can put it up here now. Give me a link. Give me a little bit of time. So it's temp./debug.ttpsm. There we go. All right. So we just talked about line 83, line 82 and 83 together. They basically just do a regular JMP to main. And then the macro on this line here. Okay, let me turn on line numbers on both sides. So on the C side, on line 9, which is a pound define, it really kind of serves about the same purpose as line 84, because on line 84 we're defining the label num neighbors to be basically doing the same thing as a macro. Every time the assembler sees the symbolic name num neighbors, it would just replace it with the value of 4. That's all it does. And then we have cell flags, cell n, and we are forgetting, we don't have a size for cell, so we might want to add that. So I'm going to put a bookmark here and see if there's any references to size. And there we have it. So we know that we are supposed to also define the size. So we'll go ahead and define it on the C side. Okay. Oh, okay, there we go. And we are at the right place already. All right, so but before we do that, it is important to understand, are we defining the labels correctly? The first member is flags. Okay, that's good. It has an offset of 0 because it's the first one. The second one is n, which is flags 1 plus. And that's correct because this 1 here is referring to the size of flags, which is just an unsigned 8-bit integer. So that part is fine. Now we have to define cell underscore size, and that's going to be cell underscore n, which is the offset to member n. But this time we have to be careful, in terms of how many bytes is the member n going to take up. So we can see that this is an array, and it's an array of 4 items, and each item is a pointer. So that means we only need 4 bytes in this case. So a 4 plus is going to be correct in this case. All right. So that defines the cell structure, and then we there's a constant here that says bin here equals to 1, and it is so there are 2 ways to do this. Okay, it depends on whether we need to refer to the address of bin here. If we need to refer to the address of bin here because we might pass the address of bin here as a const uint underscore t to somewhere, then this is not going to work. Okay, we got 2 questions here. Num neighbors. Yes, that would be, yep, there we go. Num neighbors. Okay, very good. Good job, Nathan. All right, good job, Darvish. So bin here, we can use 1, as just a label, but then it all depends on how we refer to bin here. So I'm going to put a bookmark here again, and then we'll look for references of bin here. And it's just being used as a constant, and constant. So that's fine. Okay, so just using a label as 1 is going to be okay to define bin here. So now we get to DFS, which is depth first search. Okay, that's what it is. So depth first search has so we first look at parameters. It only has 1 single parameter, which is PC, and PC is going to be defined as the last one. And then it has local variables. In terms of the local variables, sometimes I define the first one having the highest address, sometimes I define the last one having the highest address. It doesn't matter which way as long as it is consistent, okay? So in this case, I'm defining PTR to have the lowest address and then followed by count. So that's why PTR or pointer has an offset of 0 from where the stack pointer points to once the frame is fully constructed. And then PTR is, and then count is the next one. And because this is a pointer to a pointer, which basically is a pointer of some kind, so it only takes up 1 byte, and that's why we have a 1 here. And then count is right after that. So DFS PTR 1 plus is correct. Now we have to look at the total number of bytes that we need to reserve for local variables. So that would be DFS underscore count 1 plus, and that is correct as well. All right, so now we have to define PC, which is our parameter. The parameter is going to be DFS count 2 plus, which is not wrong. Okay, you can look at it as DFS local var length 1 plus. That would be fine too. Or you can look at it as DFS count 2 plus. That would be fine as well. Because in between the count, in between the starting point of the count and PC, there is the return address. So that's why it is a 2 plus, not a 1 plus. So far so good. Now we okay, this part is kind of interesting. So the first thing we need to do is to allocate for the local variables. To allocate for the local variables, we are supposed to subtract local var length from the stack pointer. So we are missing that instruction. So we're going to have to insert that. So we say, so when you're inserting in a program like this, the instruction says you have to follow a particular format. So just be careful when you're doing this, okay? Because you're supposed to put in some comment to indicate how you're adding to the existing code. Let me point you to the instruction part so that we are clear on the convention. Okay, so if your line is missing, add it and comment starting with the word inserted. If only a part of the line needs to be changed, then you say it is changed. If not, if you're adding, if it's removed, you comment it out and then you say removed. If you add, okay, where is the part where we're inserting a line? Right there. So when we add a new line, it is inserted. So using that convention, this one is inserted, and so is this one here. This is also inserted like that. So this convention helps me to identify, which part is your answer and which part is in the original code. Because without, commenting like this, it would become very difficult for me to locate the changes that you have made. More or less, okay, because I got a tool to kind of help me locate differences between the files. Oh, okay, I'm glad you're excited. All right, so now we have so now we are on the next line. We need to initialize count. So we have the typical thing, LDIA with DFS count. So A is the offset. We add the stack pointer to A. That would make the address of count. Subtract CC would zero out the content of C, and then STAC is going to store the 0 into count as a local variable, and therefore accomplishing what line 20 is trying to get done. So that part seems right to me. And by the way, in the final exam, you are allowed and encouraged to utilize all the tools that we have talked about in this semester. So that would include the assembler, LogicSim, and also the trace analyzer. If anyone wants to use Jonathan's tool, you're more than welcome to use that tool as well. So, tools are fine. I don't really have a problem of people using tools in the exam. Online GDB, perfectly okay. The only thing that I absolutely cannot tolerate would be collaboration during the test. So that is definitely a no-no. But if you want to use tools, go ahead. If you need to look up definitions of terms, you can go back to the various resources that we have used in this class. I really doubt Google can help you much in this case. But you're free to Google it too. Let's see. My only issue is using Vim highlighting, but not using copy and paste. Mm, not quite sure what. Oh, okay. I see. I see. Yeah, there's no key binding in Google Doc to use the VI key binding. That's kind of a shame. Maybe Omar can write a Vim to Google Doc sync script. So we will just edit locally using Vim, and then the script will mirror those changes, in real time, more or less, to the Google Doc. That would be a cool project for Omar. Omar is really good at Google scripting, by the way. Just, just in case you guys don't know already. All right, so we are done with line 20. And then now we're moving on to line 21. So line 21 wants to check PC first, not what it points to, okay? Just the pointer itself to see whether the pointer itself is null or not. So that would be this part. And by the way, if you're on the debugging, type of question, you can always insert new lines. If it makes things easier to read, you can always comment on each and every single line if that helps you understand what is going on as well. So on line 102, we are loading the offset of PC into A, and then here we got the address of A, and then here we got the value of A, and then we use AND AA to potentially set or clear the Z flag, and then we utilize the Z flag to help us branch. Okay, so far up to line 105, everything looks good to me. Exactly. So Chris, you're correct. So you need to So I'm not focusing on the commenting. I'm just kind of be focusing on the answer part, because the commenting part may change depending on the exam. So make sure that you read the exam instructions carefully before answering too, because I don't want people to really spend all the time answering, but not in the format that is required. All right. So here we have a JCI to DFS if one end. So at this point, I need to make sure that if one end is really the end of the conditional statement, because it is possible that the label does not reflect what it does. So I'm gonna fast forward a little bit and find the label if one end. So we can see that if one end is indeed at the very end of the subroutine, because we see that we are loading whatever the stack pointer points to retrieve the return address, increase the stack pointer, and then jump back to where we came from. But I already found a problem here because I did not deallocate the local variables. So if I don't want to deal with it now, I can just put a to do here. I'm going to say to do deallocate local vars from the stack, because this is not my focus. I don't want to get distracted, so I'm just leave a note. I'm leaving a note here, and then I can go back to where I came from, which is here. If you, oh, I can't. Never mind, since we're not using VI. In Google Doc, you can actually use bookmarks too. There's a way to do it. I think I'll get to that later. Okay, but there are ways you can define bookmarks and reference bookmarks as well. So that way it's easier for you to kind of go back and forth between the code. All right, so I might want to just kind of leave behind some comments here and say this is the then portion of the conditional statement. Okay, just so that I remember that. Okay, because if I don't comment stuff like that, it's going to be difficult to remember. But that's actually not the case. I lied. The next one is going to be the right hand side. Okay, RHS of the and operator, because all we did was to check the PC, but now we also have to check the second condition here, which looks like a mess to me, right? But we'll deal with this one level at a time. Okay, so the key is don't let the complexity of the expression um, affect you, emotionally. Instead, just kind of look at it and go like, okay, I know how to do this. Okay, it has to be able. I have to be able to break this down to one step at a time. Okay, so we'll do it one step at a time. The first thing we need to do is to look at this statement here, and I have explained it many times already. We are trying to get to the value of the flex member of the structure the PC is pointing to, which means I need to get to PC first. Okay, so um, here's the looks like there's an assumption that A is PC already. So now the question is register A actually PC? The answer is true, okay, because up to this point, this is how we check whether PC is null or not. So we know that register A should have PC in it. So that means if I just add the offset of member flags to the address of the structure, which is in register A at this point, because PC is a pointer, right? Because PC is a pointer to a struct cell, so that means PC really is the address of the first byte of a struct cell. So by adding the offset to a particular member, in this case flags, to the address of the entire structure, I get the address of the member flags in this case. So now I dereference it. I put it into register C. So register C should now have the value of member flags of the structure that PC is pointing to. Okay, there we go. So I might want to say that here, because if I don't, I'm gonna forget what it has at this point. So I'm just gonna write it down here. Because the one thing you might realize is when you're working on something like this, you might lose track of what was the last line that you were working on. Okay, so by using commenting, it is helpful to help you remember where the last line was that you worked with. Yes, there's a vacuum cleaner running in the background. Oh, that's okay. That's my son cleaning up his area. It's okay, Luke. Okay. Changing the font is fine. No worries. You can always change the font. Instructions begin on line 54. Yes. Yes, Chris. Okay, very good. Thank you. All right. So now we look at flags, and we want to know what are we supposed to do with flags. We're supposed to do a bitwise AND with bin here, and we already know the bin here is really the label itself is the value, right? So we put we do a LDIB bin here, so the register B now has the actual value of bin here, and then we are supposed to perform a AND operation, but this AND operation is ANDing the wrong thing, right? Because it's doing AND CC, which is not going to be useful. We need an AND BC or AND CB. So we have a choice here. Okay, so I'm going to say, AND BC or AND CB as a question mark, because it might make a difference depending on whether we make assumptions later on about what is in the registers. So we look at how it is branching. The JMP, the JZI to if one end, basically because this is there's a negation here, which basically means if this is null, then we proceed forward. Okay. So if it is null, then we proceed forward. That means the polarity of these two labels is incorrect. Because in this case, the JZI, basically means, if the bitwise AND results in a 0, we go to the end of the conditional statement. We skip everything. But that's opposite to what we actually want to do. Because, if it is not null, let me see, double check. If it is null, then we want to proceed. If the result of the ampersand is null, then we do not want to proceed. Yep. So the polarity of these two labels are actually incorrect. So I'm gonna put a changed to if one then, and then this one will say changed to if one end. Okay, so that's the change here. So there we go. Now the other thing that if this is the kind of question that you are getting, the other thing that you can also do is to have your own revision control. It doesn't have to be GitHub or anything fancy. If you just want to save the file multiple times, and each time you save it with the timestamp on it, that's a very crude way of getting it done. Okay, that's fine. All right. So if it is 0, we get out. If it is not 0, we don't get out. So that means when we get to if one then, we have to check here to see whether register B and C are supposed to have existing values, and they're not, because on line 116 and on line 117, we are changing the register values, B and C already. So there's nothing that we need to leave behind, which means in this case, the end CC can be changed either way, because we don't really need to know. We are not maintaining the registers. Okay. So typically, I would put the result into B, because B is really just a constant. It's basically a bit mask, so it really doesn't have any particular value beyond the bitwise AND operation. So we're going to change this and say changed to AND BC. And of course, the reasoning, I'm not typing the reasoning because I'm already explaining it verbally. All right, so now we get to line 116, which is the beginning of the actual then branch. Okay, so I might want to comment here and say this is the beginning of the then branch. There we go. All right, so line 116 is corresponding to line 23 here. So line 23 is trying to do a bitwise OR equal to with bin here. It's basically boiling down to the same thing as flags or bin here, and then you store the result of that back into flags, as the member of the structure being pointed to by PC. Alrighty. Alright, so but right here we are using register A again, and do a dereference. So now we have to go back and check, okay, do we have the address of the flags member of the structure pointed to by PC in register A. And we can see up here, the only reason why this register C has the value of flags of the structure pointed to by PC is because A has the address of the member flags of the structure that PC is pointing to. So that seems to me is a valid assumption. Okay, so we'll say A is still the address of the flags member of the structure that PC is pointing to. So that will make B the actual value, right? So, and in the next line, we are loading bin here into register C, and then we perform a bitwise OR operation. And the order of these operators is important because whatever register is getting modified, it should be the one being used in the ST instruction, which then stores the result of the bitwise OR back into the flags member of the structure that PC is pointing to. Okay, that seems to get everything done so far. So I will even leave behind a little bit of a comment here and say this is the end of line 23 of the C code. Just because if I go back to look at this code again, I might kind of lose track of stuff, right? All right, so next is we are doing something with flags. All right, so something is definitely wrong here, right? Because and then here's the beginning of the while loop. So it looks like I'm not incrementing count at all. Okay, so I'm missing the entire line 24 of the C code in the assembly code. So now it's time to, get that fixed first. All right, so we're going to have to insert code for line 24 of C code. So this is really just comment for myself, okay? Just so that I have the context of what I'm about to do. So we have LDI. Looks like we don't need to keep track of the other registers, just from the looks of line 125 to line 129. Because register C and register A are both getting. Oh well, hold on a second. Register A is still being used without reloading, so I might want to leave register A alone, even though I'm pretty sure that is not, well, actually it is the case. So I'm gonna leave register A alone for now. We'll just use register B and C, just because I can see on line 126 that we are making certain assumptions that register A still has something important in it. Okay, we'll not skip register A, use the other two. So we're going to use register B in this case for BFS underscore count. I think that's the label name, but it's not finding it. Oh, DFS count, not BFS. Okay, breadth first search versus depth first search. Well, this is the kind of confusing that I get when I'm teaching 440 and 310 at the same time. Because in 440, we are talking about Dijkstra's algorithm, which is essentially a breadth first search type of algorithm. That gives me some idea for this test. I'm just kidding. Just kidding. Okay, so we are loading the offset into B, and then we add the stack pointer to B, so that B becomes the address of count. And then we do LDAB. Oh, cannot use A. Let's use C. So now C is the value of count, and then we'll do a increment of C, and then we'll store it back to the address of count, which is still in register B. So there we go. So this should complete. Okay, end of line 24 of the C code. There we go. So we got some more comments coming, and okay, well, it's breadth first search is, it's actually, it's not really that complicated when we get to that in 440, not in 310. All right, so now we are on to line 25. So this would be the beginning of line 25, and so the first thing is, what are we doing here? Okay, we have cell and cell flags, and then a minus. So the reason why this is the case is because register A, last time we used register A is on line 120. At that time, register A has the address of the member flags of the structure that PC is pointing to. On line 25, we need to refer to the member N of the same structure. So what we need to do is to subtract flags as an offset from register A, and then we add the offset to N to register A. So this is a kind of shortcut to do it. We basically compute the differences between the two offsets and then add this difference to register A. So basically the idea is, by this time, register A should have the address of the member N of the structure that PC is pointing to. So that is that's the idea. Okay, so this is okay. So if you take a step back, okay, it's very important that you keep track of what is in each register, basically throughout this program. Because if I didn't keep track of what is in register A, at this point, and I did not leave behind some comments, on line 117, it would be very difficult for me to find out, what line 129 and line 130 are trying to do. And the the question also states, if people make unnecessary changes, that would be counted as errors as well. Okay, in other words, people are not supposed to, just go like, I don't understand this block of code. I'm just going to replace it with something that I write. That is actually not okay either. So people are not supposed to change code that is correct to begin with. All right, so that makes the test a little bit harder, but I really want to see that you guys can do what I am doing right now, is to keep track of what is in a register basically throughout the entire program, because we should be able to do it. All right, so now we get to, and then the first element of an array has the same address as the array itself. So that means register A has the address already, and then this ampersand, is done. Okay, because remember in C, what you see in C and C++, using the ampersand or address of operator seems like an additional operation, but in assembly it is the opposite, because you have to get to the address of something first before you can get to the value. In this case, register A on line 130 already has the address. Okay, so we are done with the left hand side. What is left to do is to copy that to PTR, which is a local variable. So we load the offset of the local variable into C. We then add the stack pointer, so now we have the address, and then we copy register A to where register C is pointing to, and therefore completing line 25, end of line 25 of the code. So now we have the loop down here. So the loop it also looks really ugly, because it looks like we are doing some pointer stuff, some arithmetic, and then some comparison. Once again, do it one step at a time. So in the assembly code, the first thing I do is to get to PTR. So we have the address of PTR, but there's no dereferencing yet. So that means I'm missing a dereference here, because later on I do a CMP/CA on line 142, and I would be comparing the address of PTR instead of the value of PTR in that case. So I now know that I'm missing a LDAA. So on line 138, it has to be a part of the right hand side of the comparison. So now we have PC, and then we have the address of PC, which is the address of the structure itself. And then we only want to access member N. Okay, so now the question is, do you know how to do this calculation here? This is pointer arithmetic. In this case, pointer arithmetic is not too bad, because N is an array of pointers. So when you have an array of pointers and each pointer only takes up 1 byte, then whatever num neighbor is, or whatever num neighbors is, you just add that, because you have 1 byte per element in the array. So that makes the pointer arithmetic a little bit easier to do. And we can just do it in here, because all we are trying to do is to get to 1 byte past the end of the array. So we have cell n as the offset to the beginning of the array, and then num neighbors is the number of elements in the array, and each element is taking 1 byte. So when we add these two, we are back getting to 1 byte past the end of the entire array, which is what the C code wants to do. Okay, because the C code is trying to define the boundary of where PTR can go up to, but not equal to. So that would be the correct offset to load into register B, and then we add B to register C, and that would not be correct, because register C at this point has the address of PC, and I need to know what PC is pointing to. So that means I'm also missing an LD CC in this case, because I need to refer to the value of PC, not the address of PC, when I add the offset in register B to register C. Whew. Okay, so that means register C on line 142 should have the right hand side of the comparison, which is 1 byte, the address of the 1 byte that is past the end of the last element of the array n, of member n of the structure the PC is pointing to. Whew, that is a mouthful. So then we can do a compare. So when we do a compare, once again, we have to be careful here, because which way we compare and what flags do we pay attention to, both of those are important. We want to stay in the loop when PTR is less than. So PTR is in register A, and the other one is in register C. So we know that we are supposed to compare register C to register A. And if register C, which is the right hand side, is less than PTR, we definitely want to leave, because that would mean PTR is greater than the other side. But JLI is incorrect. This has to be JCI, because pointers are not signed. When you cross over from location 7F to location 80, guess what? Location 80 is considered at a higher location than location 7F. So we should be using unsigned comparison, which means we have to use JCI instead of JLI. Okay, I'm hoping you guys still remember those flags, okay? Because there's no way to truly make the exam non-comprehensive, because everything that we have been building, I shouldn't say everything, but a lot of things that we have been building in this semester, they are still being utilized, okay, as fundamental concepts, of how to write a program, how to translate a program from C to assembly. So there's no easy way to kind of go like, oh, we don't need to know that stuff anymore. We actually still need to know that stuff. Okay, so JCI is good, but we're missing one thing. What about when they are the same? What if PTR equals to the address of the byte, that is just right past the last element of member n of the structure that PC is pointing to? Okay, so we need to add a JZI here to the same label, which is while one end. There we go. So now we are good, okay? Now we are catching both conditions to get out of the loop. All right, so David is typing something, and I'm gonna wait so I can finish my coffee. Well, the next sip anyway. All right, so the question is, why don't we need to dereference after line 142? Because n itself is an address of a pointer, and this is comparing the end result of this expression is an address. It is not the content at that address. That's why we don't need another dereference after line 142. So that's a C concept issue, not an assembly language issue. Okay. All right. Okay. So here's the next level. Okay, so to answer that question, I would encourage you guys to actually compile and run this program, and then put a breakpoint on this line, and then in the debugger, go ahead and print whatever this expression is. Then you will understand the type of that expression. What is the type of that expression? Because the type of the expression will tell you whether we need to do a dereference or not after line 142 in the assembly language implementation. So that's my recommendation, okay, is to understand the C code, and one way to understand the C code is to use the debugger. You are free to use the compiler, the C compiler, and the C debugger. So use that resource to help you understand what is the type of an expression, because that will tell you, whether you need to dereference or not. All right, so we have now, what is left is the body of the loop, which is on line 28 of the C code. So line 20 of the C code is going to be this one. It's a LDAA. So that is making an assumption that register A has PTR in it. And we will double check, right? So PTR, this is the address, this is the value of PTR, and this is dereferencing it one more level, which is fine because this is exactly what the C code is trying to tell us to do, is to dereference PTR. So this is correct. We push that on the stack. Okay, we might want to leave behind a comment here and just say that this is pushing whatever PTR is pointing to on the stack. And then we push the return address on the stack. This is correct. And then we branch to the subroutine. And then when we get back, we deallocate the argument. So far so good. What is this doing here? Looks like there's an extra increment D here. At least that's what I'm suspecting, because I'm not aware that we have pushed anything else on the stack. So this is extra. Okay, so we need to remove this one. Okay, only one argument in this case, so we only need to deallocate 1 byte, not 2 bytes. All right, so after that, we need to use whatever DFS returns and add that much to count. So we have to calculate the address of count and get to the value of count, and then we add the return value of DFS to the current value of count and then store that back into count. Looks good to me. Okay, so I'm going to call this one end of line 28. Now we're on to line 29. So we have destroyed the address of pointer already, so we have to recompute it. So line 161 and line 62 together is computing the address of PTR, and then we get the value of PTR into register C, and then do a plus plus here. Okay, so now we have to be careful. What is the type of PTR? The type of PTR as defined on line 19 is a pointer to a pointer. So that means one level dereferenced, it is still just a pointer. So we are not supposed to add the size of a cell to the pointer because PTR itself is a pointer to a pointer. So we are not incrementing by the size of a struct cell. We should be incrementing by the size of a pointer. So that should just be a 1. Oh, right. Yeah, this is supposed to be count, not counter. Thank you. Yeah, this is one of those things where the assembler can catch, but visually I cannot catch it because the syntax highlighting is not sophisticated enough to catch those. Okay, so we're going to change this to changed from cell size to 1, and I could have just incremented, that's fine too, but I want to do the minimal changes to the program. So now we store the result back into PTR. So that looks good. Okay, this is end of line 29. Now we have a problem because we're supposed to be at the end of the body of a loop, which means we need to go back to the beginning of the loop at this point, and there's no JMPI right here. So we need to add the JMPI instruction back to DFS underscore while one begin. There we go. Because otherwise it's not going to be a loop. It will get through once and it won't iterate through again. So now we're at the end of the conditional statement about to return, which also means it's time to deallocate the local variables. And we're also supposed to return count as well. So we got 2 things to do. Copy count to register A, because that's how we return a value. All right, first thing first. We need to get to the value of count first, because once we deallocate the local variables, count is gone. Okay, so that's kind of, so I need to specify these operations in this order. All right, so we'll do it one step at a time, right? LDIA with DFS count add AD, and then we'll do a LDAA. Okay, so that should specify the return value. And now it is time to get rid of all the local variables. So we can do an LDIB with DFS. I think the local var length is the label of that represents the number of bytes on this, the number of bytes of local variables, not of the entire frame, just the local variable portion. So we load this, and then we add that much to the stack pointer to deallocate, and then we can load whatever the stack pointer points to into register C, deallocate it, and then JMPC to get back to the caller. All right. So that should debug DFS. And now we move on to the rest of the program. All right, so we are defining C4, C3, C2, C1, and we'll just double check, right? We got 0 and then 0, 0, 0, and then the ampersand of C3, but because these are statically allocated, because all global variables are statically allocated, which means the label is the address. So that is correct. And then we get to C3, all zeros. Okay, that matches the all zeros, all 5. Then we get to C2. We got a 0 and then a C1, C4, and then a 0 and then 0. So that looks good. And now we're getting down to C1, which is 0 and then C2, 0, C3, and then a 0 again. All right, so everything looks good. I'm not even sure whether main needs to be debugged or not. I guess we need to debug it because the end of the faulty TTM ASM code ends here. So that means main is potentially buggy as well. So might as well check it. Alright, so main is rather simple. It only has one single local variable, which is counter. So this is just to initialize the stack pointer, typical things. This is the offset to the local variable counter once the frame is set up. This is for setting up the frame. So far so good. And I always check, it's a good habit to check the end to make sure that we are deallocating the local variable. So that is also checked. All right, so now we, let's see. So register A has the address of counter, and then C becomes 0, and then we are storing the 0 to counter. Okay, so that would accomplish line, oh, that's initialization of counter, which is not needed. Huh. Okay. All right, so now we have this code here. Okay, so I did something extra that is not needed, which is the initialization of counter. That's not needed. Over here, we are calculating the address of C1. This is not right, okay? Because once again, C1 is statically allocated because it's global. So that means the label C1 really is the address of C1. So it's not relative to the stack pointer because it's not living in a frame. And as a result, line 220 is not needed. So this line needs to be deleted. And then we push the address of C1 onto the stack. That's good. Then we push the return address onto the stack. That's good. Then we continue execution in the subroutine. And when we get back, we should be getting back here. So when we get back here, we need to deallocate the argument. So we forgot that, right? So increment D should be here. This is inserted. And then we need to store the return value of DFS into counter. So we compute the address of counter, and then we store the return value of DFS into the counter with the allocate counter itself, and then we get to the halt instruction. So Aaron has pointed out something that is different from what we have seen before, but I think you guys should be able to identify why it is not a .6 plus. Exactly, so Marco is correct. Because I switched the order of the decrement D versus the LDI instruction. So in this case, we do not count the decrement D instruction as part of the distance between the LDI instruction and where the subroutine is supposed to return to. Yep, exactly. Good job, Marco. Yeah, so gotta be careful with these things, right? So I will throw these things into the program. Obviously, things that you're seeing here in this particular program, I might still be using some of those, obscure things, but chances are, I will try to think of new obscure things to throw into the program. Line 25 in C. Let's see. Alright, so line 25 of the C code. Because we are looking at the address of whatever this thing is instead of the value. So the address of typically says, you don't do a dereference. Is that okay? Or are you referring to the other side here? Okay, so let me check. Let me check that code on line 25, right? Well, good thing I left behind some comments. Well, here's my dereference. Yeah, I dereferenced it right here. There are only two instructions capable of dereferencing. One is LD and the other one is ST. Yep. Okay, so yep. So it's time to test this program to see whether it gets the right thing done or not. So obviously there's no way we can test the program other than just checking whether the stack pointer goes back to 0, unless we run the C code first to find out what is supposed to be stored in counter, right? So that would be the next thing to do, is to run the code in C, just so that we can observe, the values in the value in counter when the algorithm is done. I knew somebody's going to ask that question. I'm not sure, because uploading this code, may not. I mean, obviously, the content is all here on YouTube, right? By giving you the code that I have already modified, which is the C code the assembly code over here, I'm not really sure that that's going to be beneficial. Let me think about it. So we have line 7 to line 47. So 7 to line 47. Let's write it to an extra file. We call it debug.c. And now we can go ahead and take a look at that file. Alright, so the first thing we need to do is to clean it up and get rid of all the / so it becomes an actual C program. So we look at this program, and then we replace all the first two / and a space with nothing, and now it looks clean to me. And then we'll do a gcc-o. Yeah, debug is not really a very good name, because there is. Oh no, wait, no. This is not DOS. There's no default command called debug. So that's okay. There we go. And then we gdb d. Oh, I forgot the dash g option. Now, obviously, this part you can do it in online GDB. So if you don't have GCC installed and you don't want to bother with code blocks or all that stuff, just go ahead and use online GDB. That's perfectly okay. All right, so now we debug, and it depends on how confident you are or confident you are of my coding. So we can just go ahead and put a breakpoint on line 39, like so, and then run the program, and then we want to see what is count in this case. Counter. Okay, never mind. Counter is 4. Okay, so the assembly code should do about the same thing, right? Because even though the length of a pointer is changed, okay, and even the structure may be changed a little bit because in C it might do some padding, but the algorithm has not changed. Okay, so we should still be seeing a number of 4 in counter at the equivalent part of the assembly language program. So now here is the moment of truth, right? Because now we are going to run the assembly code. All right, so let's go ahead and copy the assembly code to the clipboard. And then we get to our trusted assembler. I'm not sure whether this is the assembler or not. Nope, that's also from a different class. Yep, see, I told you about Dijkstra's algorithm. This is how we do it in that class. Yes, I like to use spreadsheets. Yes, that part is true. All right, so get rid of everything and then paste the code in and let the assembler do its thing. Well, the truth is Google Sheet can run JavaScript because Google Script is basically JavaScript. So whatever I can do in JavaScript, I can basically do quote unquote do it in a spreadsheet too. That's actually how I cheated to get some of the symbolic processing done. Yep, there we go. I misspelled while one and. Okay. Alright, so while one and. Okay, fix that. I should probably fix the C file too in case I'm uploading that later on. And I did say in case. I did not say that I'm going to upload it. I'm just saying that in case. So I think I misspelled it as. How did I misspell it? W-E-I maybe? I can't remember. Let me see. Where is there? There are the 2 consecutive jumps and one of them is wrong. There we go. There we go. Alright, so I'm going to fix that too. Alright, back to the assembler. I think it's good now. Yep, looks good to me. Go to RAM file, and it says it's good too. And you might be alarmed that you're not seeing any code. That's because the first part of the program is a whole bunch, big chunk of comments, that talks about how to format your changes and how this is going to be scored, da 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 da. And the entire C code is also at the very beginning, so that's why it looks empty because all the assembly code, the opcode comes later. All right, so we download to CSV. To get back to Chris's point, I got one comment on that. When you have a hammer, when the hammer is all the tool that you have, that's kind of how I see a spreadsheet. Uh-oh. It is not responsive. Huh. Alright, what is going on? I can still click, but my terminal, it is still responding to keystrokes. Now it's okay. Ah, okay. Alright. Alright, so we're gonna run this. And the program is called debug.csv. And then we capture the output into debug.tsv. And this is also something that you can do. Oh, this it's not looking good because it looks like it got into an infinite loop of some kind, and it waited all 3 seconds. Or it's also possible because my CPU load is pretty high, and it just took longer than usual to finish. We'll see. So now we get to the trace analyzer and find out what is going on here. Alright, so we get to sheet 1 and then do an import. Alright, and then just upload our debug.tsv. And do the usual stuff, replace current sheet. So if you're using Jonathan's tool, you wouldn't have to do all of this stuff here, because it gives you the trace as it executes. I think it assembles and runs in one single command. Is that right, Jonathan? It's the super streamlined way of doing things. Yep, there you go. So yes, you guys can use Jonathan's tool, and I'm just too lazy to learn a new tool. I'm sorry. I'm just too lazy to do it. All right. So it looks like this is longer than it needs to be. So we'll look at summary first. 4050. Okay, so I'm fairly sure that we have some kind of a loop here. Okay, but that's okay. 4050, 4050. Okay, so we get to the end first. So we are definitely not stopping at a halt instruction. Instead, it went to location 5. So I want to see if we are seeing a repeating pattern, right? Because if you see a repeating pattern, then you know that you're stuck in a loop of some kind. So it does look that we are stuck in a loop of sorts, where the first part of the loop is at location 3-1, and the last location of the loop looks like to me is location 5-9. So now we used this as a clue, okay, to find out, all right, where in the program are we talking about, right? So this is how we debug, okay? Maybe in the entire lecture, okay, this part, I wouldn't say this part is the most important because I think most people would not even try to run the program, okay? Which is, I was expecting most people to be able to at least get to the this portion of the debugging, instead of just looking at the text file. But that did not seem to be the case in past semesters. All right, but I'm going to do it this way. So we get to the Assemble tab, and then we look up column W, and then we look up 3-1 because 3-1 is supposed to be the beginning of the loop. Aha! Okay, guess what? This is exactly where where 1begin is. So I have a strong suspicion that location 5-9 is the JMPI back to this location. So now we look up location 5-9, and guess what? It is exactly that. So we are stuck in the loop. Okay. All right. So now you have to ask yourself, what do we do now? There's so many instructions in the loop. How do we know which one is wrong? Blah blah blah. Right? I mean, those are all very legitimate reasons, okay? How do we debug a program? Now that we know It's not the worst case scenario because we don't have an endless recursion. We simply have, seems to have an endless loop, situation. Now, I did not actually verify that we did not have a endless loop, endless recursion situation. So let's double check that that is not the case, okay? Because that will be indicative by register D getting to a very, very small value. So we want to look up how register D is changed. So even at the very end or so, register D is still at location FB. That tells me that we are not having an issue with an endless recursion, because an endless recursion will continually consume stack space, and register D is going to get lower and lower and lower and lower. FB is not low at all. I mean, that's not very low. So, and we can also reconstruct the map to the stack, but we'll get to that point, because right now I'm not suspecting that is the issue. So that's why I'm not going to pursue in that particular direction, not yet. Okay, so now what we need to do is to look at the C code and basically question ourselves of what in the high level logic, what is going to cause the program to be stuck in this loop here. So we are basically looking from line 26 to line 30, which really only have like 3 lines of actual code. We can see that the one thing that will help us get out of the loop is by PTR incrementing. So if I, for whatever reason, forget to increment PTR, then it'll be stuck because PTR has exactly the same value every single time, and it's not going to get out. Or the way I'm comparing, okay, the way I'm doing the conditional branch, if those are incorrect, it can also potentially cause this program to be stuck forever. Okay, so I'll be checking those things. So on the assembly side, the first thing I check is whether PTR is incrementing or not, because it is my favorite mistake to in my programs is forgetting to increment the pointer at the end of a loop. So I would be checking that first, but that's only because that is my favorite mistake. So you may not go you may not go in this direction. All right, so line 161 is the beginning of line 29 in the C code. We compute the address of PTR. Okay, so we LDR, we get to the value of PTR, and then we add 1 to the value of PTR, and then we store that back to PTR. So it does seem to me that I am indeed incrementing PTR. So that means whatever the problem is can potentially be not evaluating PTR correctly when I'm comparing. Okay, so here we have the address, then we have the value of PTR in register A, and then on the other side, wait, hold on a second. Oh, okay, that's fine. So now we need to evaluate the right-hand side of the comparison. So we first get to PC, we get to the value of PC, which is the beginning of a structure, and then okay, that is why. Oh wait, hold on a second. And then we get the offset. Oh, okay. Yeah, so we have the offset of member n, and also the constant that we want to add to that offset, which is num neighbors, added to register C, which is the value of PC, which is the beginning of a structure. So by the end of this add CB, we should have the address of the byte right past the end of member n of the structure the PC is pointing to, which is what the C code is referring to do the comparison on line 143. And if register C is less than register A, we get out. So that means if the right-hand side is less than the right-hand side is less than the left-hand side, we get out. That is correct. If they are the same, we also get out. Okay, so that looks good. So, just by looking at the code, I'm kind of stumped. So that means, the trace analyzer will be the next thing that I'm going to use for checking this. So we have to go back to location 3.1. Oh, so the other thing we can also do is, all right, so we can also see that we got out of the loop because we somehow got out to location 6.4, and location 6.4 is most likely the JMP instruction to get back to um, the caller. So that means, all right, so that means, we may not have an infinite loop issue. All right, okay, so let's go back to, because I just checked the conditions, they seem to be evaluated correctly. So let me see if I can find some other clue. Okay, so right here, this is the most suspicious part is we are getting to location 0.5. So I'm suspecting 0.5 is the beginning of the subroutine. Alright, so let's go back to the assembler. Oh, we are almost running out of time too. Let's see. Location 0.5, that's right. Okay, I have to keep track of what I'm doing. Yes, so the location 0.5 is indeed the beginning of the subroutine. So it is right about to call itself again. So it's also possible that I just did not give it enough time to finish. That's possible, although that is a little bit unlikely. The C code does complete, but the assembly code did not. Alright, okay, so we'll do one more thing. And this time I'll let the program run a little bit longer and see whether it finishes or not, because it's entirely possible that the timeout of 3 seconds is just not enough. So that means, I've been wasting my time, if that is the case, chasing, this is a, this has been a wild goose chase, if that was the case. Yeah, so that was my bad. it just it just took longer than 3 seconds. Let me find out exactly how many seconds it took. Yep, sometimes I do stupid things like that. It took 3 seconds, 3.416 seconds, and the program timed out itself at 3 seconds. So we were off by less than half a second. The program basically, the timeout made it give up, half a second too early. So the program did not quite get to the finish point. And just barely too. Yes, yes, absolutely. Yep, yep. That sort of stuff happens. So now we'll just do it import again. It doesn't mean the program is not faulty. Okay, it just means that it's not stuck in an infinite loop, as I suspected. That's all that is. Okay, so we are not jumping. I am not jumping to the conclusion that the program is good. It's fine. I'm only saying that it did come to a point where the program stopped. Alright, so we'll do it again. Yeah, my system load is pretty high, so that may be a reason why it's taking a little longer than usual to get things done. Alright, so let's see how long the trace is. 4,800, so we have about close to 900 rows more than last time, which is not a whole lot. I mean, so we'll see. This is the moment of truth. What was it again? 800 something? Let's call for 900. And let's just scroll back a little bit to find. Alright. So the program ended with the stack pointer being 0 and it ended at location 90 in hexadecimal. So we want to, I'm fairly sure that's our halt instruction, but we'll double check. Just because I'm fairly sure doesn't mean it is the case. It is the case. So now we want to see whether it stores 4 into counter, okay? Because that really is the more definitive answer, and the answer is yes. Whew, okay, so I was just, chasing. It was just a wild goose chase for the last, I don't know, what, 5-10 minutes, by analyzing the program, but it is not it's not time wasted, because if you run into this situation, I have just given you some clues of how to analyze the program. Okay, how to analyze the program. Go like, okay, check this first, check that first, and see whether it is the case. And then go like, wait, hold on a second here. It did get out of the subroutine. It did get back to the caller. So there we go. Yeah, well, I'm hoping you guys have a hard drive that's big enough. I'm just kidding. Okay, that part is really just kidding, because if you look at the size of the file, I think a -U. There we go. Nope, -L. Yeah. So even the when it's fully done, it's only 413 kilobytes, which by today's standard is not too big of a deal. Okay, now if we were using floppy disks, okay, yes, it is a big deal, because it's going to take a long time to copy 413 kilobytes onto a floppy disk. But you guys are not using floppy disk, right? So that should not be an issue. Let's see. Yeah, Jonathan is right. Should probably have run it before, run it a little bit longer before I could go like, let's time out at 3 seconds. But 3 seconds has been sufficient for all the cases. It's just that today, my system load is kind of high. I can show you how high it is. Top, there we go. It's not too bad actually. It's the load average is 6 something, so it's kind of like a little high on the high side. Usually it's not that bad. All right, so yes, I will upload the assembly language code and also the C program to the text channel. I'm not really sure how much that's going to help you, because I think you should try to figure out that portion, and also re-watch the video as you try to figure out whether your answer, catches everything or not, because, I think that would be very helpful. If you just study my solution, I think that may not help you as much compared to having you to work on this entire thing by yourself first, and then checking whether your answer is right or not. So, I'm gonna upload. Okay, I'm gonna zip it up first, because there are several things. So I'm gonna look up all the debug stuff. Okay. So there we go. Okay, so we'll go do a zip debug.zip, debug.c, debug.csv, debug.tsv, and debug.ttpsm. Here we go. Yeah, we don't have enough time to work on the other one, which is Tower of Hanoi. That one is just writing code from scratch. I give you the C code, and you are implementing everything in assembly. This one is a little bit more. This one is more involved, because this one has structures, whereas the other one does not have structures. Both are recursive. And there's also a reason why I emphasize recursion, because this is a firm belief of mine, which can be incorrect, which can be unfounded. But my belief is, if somebody claims to understand subroutines but cannot understand recursion, that means to me that that person does not truly understand subroutines, or just calling and returning, because recursion is not any more difficult or less difficult compared to normal subroutine calling and returning. The rule stays exactly the same. Now, if I were to ask you to write an algorithm, a recursive algorithm, to derive a recursive algorithm, that might be a little bit harder, okay? And in reality, that's not the case, because in reality, the recursive way of looking at things sometimes is easier. Okay, you look at a string as, oh, we have a character, and then what is left is a substring, which is also a string. That's kind of the way we look at recursion. Is we look at a bigger problem, we chop the bigger problem into a subpart that we can solve right away, and then a one or more subproblems where the nature of each subproblem is the same as the original problem, just the size is smaller. Okay, so I think that makes recursion sometimes easier to understand and easier to derive compared to the iterative approach using loops. Yeah, those are really old. Those are really, really old in the old FX. Those are really old. So I'm not really sure how relevant those are. Oh, okay. I did not. I don't even remember the Tower of Hanoi is posted or not. So it is posted. Okay, it's actually posted in the general text channel. So you can go there and take a look at that solution. Oh, okay, even better. Somebody found the final exam answer from last semester. Good job, Anne. Now you guys know why I always make new questions every semester. And I think it's good. That's actually good for me too. All right. So are there any questions before I take a short break? Where can I find the files so I can practice them? Okay, what files are we talking about? Are we talking about the Tower of Hanoi or this depth first search? They're in the general channel. So look up the general channel. Those were posted last Thursday. So look up the date of last Thursday. They may not be pinned, but they should be there. Alright, will there still be a video stream when I get back or just text chat? Well, it depends. I mean, it depends on how many people are still here and what the discussion is. So, I'll decide later on whether to stream it or not. Because if it's just general questions, there's no need to stream. And the solution of the Tower of Hanoi is already posted, so it's not like I'm gonna start from scratch and derive that solution. All right, so I'll be back in about 10 minutes, and so that makes it 7:10. All right, so you guys can take a break too. For some of you, I'll see you on the day of exam, which is in a week. Okay, so we are gonna have the final exam on next Tuesday. The start time of the exam is 5:45, if I remember correctly. If you want to double check, all you have to do is to go to Google and search for American River College final exam schedule. There we go. And then you look up evening classes, and you just have to know what the start time of this class is, which I certainly hope you know by now, right? So we have a start time of 5:30, which is between 4:30 and 5:55 p.m. We do meet on Tuesdays and Thursdays, so that makes May 18th our date of the final exam, and then the time is from 5:45 p.m. to 7:45 p.m. So that's exactly when we're gonna have our final exam. Make sure you remember that time. Okay, put it on your calendar. Don't forget. Okay,